Want to learn Python programming, but don't know where to start? In this complete beginner's guide, I'll show you exactly how computers work, teach you to write your first Python program, and reveal the secrets to debugging errors and designing algorithms like a pro. Whether you're a complete coding newbie or brushing up on the basics, by the end of this video, you'll have the confidence to tackle any Python project. Let's dive in. How computers think, a gentle start to programming by the programming professor. This presentation is organized into several key sections. We'll begin by discussing the role of computing in society and how computers have become central to our daily lives. From there, we'll define what exactly a program is and walk through writing and running your first Python program. We'll also cover how to recognize and fix common programming errors. Finally, we'll explore algorithm design and how to express ideas using pseudocode, a vital skill before writing real code. Computers are powerful machines because they can follow instructions at incredible speeds without losing focus, making them ideal for handling repetitive tasks. Whether it's processing thousands of records, solving complex equations, or rendering images in a video game, a computer doesn't get tired or distracted. Beyond speed, computers are flexible. The same device can help you write essays, analyze sales data, or compose music, all through software. Software is what unlocks the power of hardware. It's made up of programs, which are sets of instructions written by programmers like you. Programming is the art and science of crafting those instructions so that a computer can perform useful tasks. Even a very simple program, like one that responds to a user's input or displays a greeting, illustrates the power of programming. What makes programming so exciting is the feedback loop. You write code, run it, and see the result immediately. It's empowering because once you know how to program, you can automate processes, create tools, and build solutions in almost any field, from medicine to gaming to education. To understand how programming works, it helps to understand what's inside a computer. At the core of every computer is the CPU, the central processing unit. You can think of the CPU as the brain of the machine. It doesn't think creatively like a human, but it can follow instructions with incredible precision and speed. Modern CPUs are astonishingly powerful, containing hundreds of millions or even billions of transistors, and they're responsible for executing every line of your program, one step at a time. The CPU doesn't work alone. It depends on memory and storage to function effectively. Memory, also called primary storage or RAM, is fast and temporary. It holds data while programs are running, but the contents are lost when the power is off. Secondary storage, such as hard drives and SSDs, is slower but permanent. It retains data and programs between uses. When you run a program, the operating system loads it from secondary storage into memory so that the CPU can begin processing instructions. To communicate with users, computers rely on peripheral devices. Input devices like keyboards, mice, and touchscreens let users give instructions. Output devices such as monitors, printers, and speakers allow the computer to present information back to the user. Many computers are connected to networks, such as the internet, allowing them to exchange data with other systems. Whether you're downloading a document or accessing cloud-based software, you're relying on networked computing to make it happen. When you run a program, the CPU follows a cycle. It reads an instruction, processes it, and writes the result back to memory. This cycle, called the fetch-decode-execute loop, repeats millions of times per second. The CPU might read numbers from storage, perform calculations, send signals to the display, or wait for user input. Though these actions happen behind the scenes, They result in what you see and interact with on the screen, like moving a mouse pointer or seeing new text appear as you type. Early computers were physically massive and limited in function. One of the first general-purpose computers, the ENIAC, was built in the 1940s and filled an entire room. It was used for calculating artillery trajectories for the military. Fast forward to today, and computers are tiny and everywhere. Your smartphone contains far more power than ENIAC ever had. Computers are embedded in vehicles, appliances, bank cards, and even light bulbs. From massive data centers to wearable devices, computing has become an invisible, yet essential part of modern life. This dramatic increase in computing power has transformed industries. Factories now use robots to perform tasks once done manually. Books are written and published using software. Music and video are created, edited, and streamed digitally. We also interact with intelligent systems every day, from recommendation engines to virtual assistants. Programming is no longer a niche skill. It's foundational. Professionals in nearly every domain, whether it's biology, business, or design, benefit from knowing how to write software or at least understand how it works. To make programming more accessible and efficient, we use high-level programming languages. These languages are designed to let humans write instructions using syntax and structure that resemble natural language and abstract concepts, rather than the raw binary code a computer's CPU understands. A high-level language allows you to focus on solving problems, rather than worrying about hardware-specific details like memory addresses or instruction sets. These languages are translated into machine code using tools such as compilers or interpreters, which act as a bridge between what the programmer writes and what the hardware executes. High-level languages are essential in modern software development because they improve productivity, make code easier to read and maintain, and enable rapid development across a wide range of domains, from web development to scientific computing. One of the most widely used high-level programming languages today is Python. It was developed in the early 1990s by Guido van Rossum, who wanted a language that prioritized clarity, simplicity, and ease of use. At the time, many languages were optimized for performance or writing large-scale systems, but van Rossum needed something lightweight and flexible for automating system administration tasks. Python was designed to be highly readable and quick to write, which made it appealing not only to experts, but also to beginners. Since its creation, Python has evolved significantly. Today, it is a powerful general-purpose language, supported by a vast ecosystem of libraries and tools. The version we'll be using in this course is Python 3, which is the current standard and includes improvements to consistency, syntax, and performance. Python's popularity continues to grow due to its versatility and strong community support. Python programs can be written and run using a variety of tools. The most beginner-friendly option is an IDE, or Integrated Development Environment. An IDE gives you everything you need in one place: a text editor for writing code, a run button to execute it, and debugging tools to help find mistakes. Some popular IDEs include PyCharm, Thonny, and Idle. Alternatively, you can use a basic text editor like Visual Studio Code or Notepad++ to write your code, and then run it manually from a terminal using a command like python3yourfile.py. This approach gives you a deeper look at how the interpreter works and is preferred by more advanced developers. Regardless of which method you choose, it's important to stay organized, create folders for your projects, and name your files clearly. A classic tradition in programming is to begin with a very simple program that prints a message to the screen. The phrase "Hello, world" has become the universal starting point. In Python, this is done using a short two-line program. First, a comment explaining what the code does, and then a print function that outputs the message. This may seem trivial, but it's a critical first step. It confirms that your programming environment is working properly and introduces the basic mechanics of writing Python code. How to write comments, how to call a function, and how to display output. It's the equivalent of a test drive before we dive into more complex logic. To actually run a Python program, you use the Python interpreter. The interpreter is the part of the Python system that reads your code, translates it into instructions the computer can understand, and then executes it. In an IDE, this usually happens automatically when you click Run. But in a terminal-based environment, you run the interpreter manually with a command like python3 hello.py. What happens under the hood is that the interpreter reads your source code and converts it into something called bytecode. This is a simplified, intermediate form of your program. The bytecode is then passed to the Python virtual machine, which runs the program line by line. Understanding this behind-the-scenes process helps you grasp how Python works and what to expect when you run your own code. Once you've written a working program, the next important step is to save it properly. Python source code files should be saved with the .py extension, for example, hello.py. This tells both you and your computer that the file contains Python code. Keeping your work organized is critical, especially as your projects grow. A good habit is to create a folder specifically for your course or project, and within that, make subfolders for each assignment. This structure helps you stay focused and makes it easier to find, update, and submit your code later on. These folders are known as directories, and just like folders on your desktop, they can contain both files and other folders, giving you a flexible way to organize your work. Python also provides an interactive mode called the Python shell. This environment allows you to type Python commands one at a time and see the results immediately. You can start it by opening a terminal and typing Python 3, which launches the interpreter in interactive mode. You'll see a prompt, usually 3 greater than symbols. At that point, you can type any Python expression, and the interpreter will evaluate it and display the result instantly. This is incredibly useful for testing out ideas, learning new syntax, or debugging small snippets of code. You can even use it as a calculator to perform quick math. The interactive shell is a fantastic playground for exploring how Python behaves line by line. Although it looks like Python runs code one line at a time, what actually happens under the hood is a little more sophisticated. When you run a program, the Python interpreter first translates your source code into something called bytecode. This is a compact, intermediate version of your code, not quite machine language, but not readable Python either. This bytecode is then sent to the Python virtual machine, which executes it. This two-step process allows Python to run more efficiently and makes it possible to reuse previously compiled code. That's why you'll sometimes see .pyc files appear in your folders. They're the compiled versions of your scripts. You don't need to open or submit these. They're just used internally by Python to help speed things up. Now let's take a closer look at your very first Python program. The first line of the program is a comment. In Python, comments begin with the hash symbol or pound sign. These lines are not executed by the interpreter. They're there to help you and other humans understand what the code is doing. The second line is an actual Python instruction. It calls the built-in print function and passes a string as an argument. The string hello world is enclosed in double quotes, which tell Python to treat it as a literal sequence of characters, not a command or a variable. This combination of comment and function call introduces two important concepts: documenting your code and calling functions that produce output. The print function is one of the most versatile and frequently used tools in Python. In addition to printing basic text, it can also display numbers, the result of calculations, or multiple values at once. If you pass more than one argument to the print function, like a string and a number, they'll be displayed with a space between them. It also automatically adds a new line at the end of each printout, so if you call print multiple times, each result appears on its own line. And if you ever call print with no arguments at all, it just prints a blank line. These features make print perfect for debugging, formatting output, or simply testing your code as you build it. One very important thing to understand about Python is that indentation matters. In many languages, indentation is just for human readability, but not in Python. Python uses indentation to define code blocks, so the way you format your code affects how it runs. If you write two print statements and indent one of them by accident, Python may interpret them as belonging to different blocks, and that can cause a syntax error. This strict rule helps make Python code clean and consistent, but it also means you have to be careful. Always use consistent spacing, either all spaces or all tabs, and stick to one style throughout your program. Most editors can help with this, but it's still something you need to pay attention to. Errors are a natural and unavoidable part of programming. One of the first types you'll encounter is a syntax error, also known as a compile time error. These occur when your code violates the basic rules of the Python language. For example, forgetting to close a quotation mark or using a capital letter for a lowercase-only function like print will cause the interpreter to stop and raise a syntax error. These errors are usually caught before your program runs, which means the interpreter never reaches the execution phase. You'll need to fix the error and run your code again. It's completely normal to go through several rounds of this while writing a new program. Some errors don't appear until after the program starts running. These are called runtime errors or exceptions. A classic example is dividing by 0. Your code may be syntactically perfect, but if it tries to perform an illegal operation while running, the interpreter will raise an exception and stop the program. These can be trickier to catch because they depend on the values your program is working with at runtime. Another type of error is a logic error. Your code runs without crashing, but it doesn't do what you expected. Maybe it prints the wrong value or skips a step. These logic errors often require thoughtful testing and debugging to find and fix. To avoid these issues, it's critical to start with a clear plan. Computers are not creative problem solvers. They can only follow exact instructions. If your task isn't something you could write out step by step for another person to follow without confusion, it's also not something a computer can do. For example, telling a program to find the best-looking person who likes hiking is too subjective. A computer can't make aesthetic judgments or interpret vague preferences. Computers need clearly defined rules, and that means you must first understand the problem well enough to describe it precisely. Let's look at a problem that is clearly defined and solvable. Suppose you invest $10,000 into a bank account that earns 5% interest annually. You want to know how many years it will take for your investment to double. This is a great example of a task that a computer can solve because it involves fixed values, repeatable calculations, and a clear stopping point. You could solve it by hand, year by year, calculating the balance and checking if it's reached $20,000. It's a bit tedious for a person, but for a computer it's perfect. Computers excel at repeating steps quickly and accurately. To describe these steps to a computer, we use something called pseudocode. Pseudocode is an informal way of writing out the logic of a program before translating it into actual code. It uses plain English and simple programming-like structures, such as loops and conditionals, to describe what needs to happen. For example, in our bank problem, Pseudocode would involve setting a starting balance, adding interest year by year, and stopping once the balance reaches the target. It's not meant for the computer to read, it's for human understanding. Pseudocode helps you clarify your thinking and catch logical errors before you even start writing Python code. When writing pseudocode, your goal is to describe the steps of your algorithm clearly and logically, using structured statements that reflect what the program should do. These can include assignments like total cost equals purchase price plus operating cost, as well as control flow structures such as if-else decisions, while loops and for-each loops. Although pseudocode isn't written in a formal programming language, it should still be precise enough that someone else could easily translate it into working Python code. Indentation is important. It helps group related steps, just as it does in actual Python syntax. You should also clearly state the final outcome of the algorithm with lines like choose car 2 or report year as the answer. The focus is not on perfect grammar or exact syntax, but on making your logic readable, unambiguous, and easy to follow. To be considered a valid algorithm, a pseudocode description must meet 3 important criteria. First, it must be unambiguous. Each step must be clearly defined with no room for interpretation. Second, it must be executable. Every step must be something the computer could realistically do. And third, it must be terminating. The process must eventually stop. If an algorithm could go on forever, it won't work as a computer program. In our investment example, the algorithm always increases the balance each year, so it will eventually reach the target. Meeting all 3 criteria means you've created an actual algorithm, and you're ready to implement it in Python. Data has become one of the most valuable resources in today's world, collected continuously from websites, sensors, smart devices, and financial systems. While humans can interpret small amounts of data intuitively, modern technology generates information on a scale that requires computational tools to make sense of it. This is the role of data science, a field that blends programming, statistics, and domain knowledge to analyze large datasets. Through techniques like data mining, we can find hidden patterns, group similar behaviors, and detect anomalies such as fraud. Machine learning, a key part of data science, goes a step further by enabling computers to learn from examples, such as recognizing animals in images, without being explicitly programmed. These systems, often built using neural networks, allow us to automate decisions and predictions that would be too complex to express through traditional algorithms. Let's apply algorithmic thinking with a concrete example. Imagine you're choosing between 2 cars. One is more expensive but fuel efficient, while the other is cheaper but consumes more gas. You want to know which car is the better deal over 10 years, assuming a fixed fuel price and consistent yearly mileage. This is a perfect task for an algorithm because all the variables are known, and the steps to calculate the total cost are clear. You'll need to combine the purchase price with the fuel cost over time, and then compare the results. Computers excel at this kind of structured, repeatable problem. To solve the car comparison problem, the first step is to clearly identify the inputs and outputs. The inputs are the purchase prices and fuel efficiencies, in miles per gallon, for each of the 2 cars. The output is a recommendation. Which car offers the lower total cost over a 10-year period? This is the goal your algorithm needs to compute. With the inputs and desired output established, the next step is to break the problem into smaller tasks. Start by calculating each car's annual fuel consumption by dividing miles driven per year by its fuel efficiency. Multiply that result by the price per gallon to get the annual fuel cost. Then multiply by 10 to get the total operating cost. Add the purchase price to the operating cost to get the total cost of ownership. Finally, compare the two totals to decide which car is the better value. Structuring this logic in pseudocode helps clarify your thinking before you begin writing actual Python code. Once you've broken the car comparison problem into smaller steps, the next move is to describe each of those steps in pseudocode. This makes your logic clear and prepares you for writing actual Python code. Start by calculating the annual fuel consumption using the formula: miles driven per year divided by miles per gallon. Then compute the annual fuel cost by multiplying fuel consumption by the price per gallon. Multiply that by 10 to get the total operating cost. Finally, add the purchase price to the operating cost to get the total cost of ownership. Repeat the same steps for the second car, then compare the two total costs and output a decision. Choose the car with the lower total. Now it's time to test your pseudocode with real numbers to make sure it works. Suppose car 1 costs $25,000 and gets 50 miles per gallon. Car 2 costs $20,000 and gets 30 miles per gallon. Assume you drive 15,000 miles per year and gas costs $4 per gallon. For car 1, the fuel usage is 15,000 divided by 50, or 300 gallons per year. That's $1,200 per year in fuel costs, and $12,000 over 10 years. Add the purchase price, and the total cost is $37,000. For car 2, the math gives a total cost of $40,000. So according to your pseudocode, you would choose car 1. Testing pseudocode like this helps ensure your logic works before translating it into code. Let's walk through a second example, this time involving spatial reasoning. You've been asked to tile a rectangular bathroom floor using alternating black and white 4 by 4-inch tiles. The challenge is to write an algorithm that describes how to place the tiles correctly. Start by placing a black tile in the top left or northwest corner. From there, alternate tile colors across the row until you reach the opposite wall. Once a row is complete, move down one tile and start the next row, beginning with the opposite color of the one directly above it. Continue this pattern row by row until the entire floor is covered. This is a great example of how simple logic, when repeated systematically, can generate complex patterns. Now let's write the pseudocode for tiling the bathroom floor. We begin by placing a black tile in the northwest corner of the room. Then, across each row, we alternate between white and black tiles until the row is complete. After each row, we move to the start of the next row below and begin again, starting with the opposite color from the tile directly above it. In pseudocode, we repeat this process row by row until the floor is completely filled. Each step specifies where to place the next tile based on the color of the previous one, and how to transition to the next row when needed. This structured description outlines the entire tiling process clearly, preparing us to implement it in Python if we wanted to simulate or visualize the floor pattern. To verify your algorithm, test it on a floor that's 20 inches wide and 12 inches long. Since each tile is 4 inches square, the floor will be 5 tiles across and 3 tiles down. Your algorithm should place alternating black and white tiles across each row. For the next row, it flips the starting color and repeats the alternation. By the end of the third row, the entire area is covered in a checkerboard pattern. This is a visual task, but the underlying logic is the same as any algorithm, a repeatable sequence of clear steps that leads to a result. Whether you're analyzing data, comparing cars, or tiling a floor, the principles of programming remain the same. Define the problem, describe the steps, and test your solution. To summarize, this video introduced the fundamental ideas behind computer programming and computational thinking. We explored how computers work at a basic level, what a program is, and how Python allows us to write clear, readable instructions for the computer to follow. You learned how to run Python programs, how to avoid and correct common errors, and how to express logic through pseudocode before diving into actual code. We also looked at real-world problem-solving examples using algorithms, from comparing car costs to tiling a floor. The key takeaway is that programming is about breaking problems into precise, logical steps that a computer can execute. With this foundation, you're now ready to start writing your own Python programs and solving meaningful problems with code. Thanks for watching. Let me know in the comments if there are other topics you would like me to talk about. If you enjoyed this video, please like, share, and subscribe for more content on software engineering and technology. See you next time.